Hi folks, welcome to Open Analysis Live. So today we're going to take a look at a sample that a subscriber Patrick sent in. He sent it in a month ago or so, and we only got around to it now, but it's a Gootkit sample, and he asked us to take a look at the packer for it because it was giving him some trouble. It looked like it had some anti-analysis stuff in it, and when I took a look at it, it's actually quite an interesting sample, so stay tuned for that. But before we get into that, just one quick housekeeping thing. I know we missed a video last week, and we are still trying to do one video a week, but Sean and I have a special project that we're working on that we think that you guys will be excited about, or hopefully you are. So what that means is we have to take a bit of time off from these videos to try and work on that on the side. So we may be missing stuff here and there, but we're going to try and keep to one video a week. Hopefully we can make it work somehow. Okay, so the sample we've pulled up on hybrid analysis here, and I just wanted to show you guys the process tree because this is usually where I sort of start when I want to figure out what's going on or how should I attack the packer here. So here we can see that there's the input sample, which runs a copy of itself with the command line switch -L, which runs a copy of itself again, and then there's a couple other things here. So anytime you see that where a sample is running a copy of itself with maybe a different command line switch or just a copy of itself a couple times, usually that means that it's doing some process injection. So the number one place to look for process injection is to hook create process internal W and take a look at what's actually being sent to that process after it's spawned. So I've talked about that in a bunch of different videos where that's like a good place to start if you see something like this where it looks like there's going to be some process injection. The cool thing about this sample is that there's definitely more going on under the hood. So what I'm going to do is I'm going to flip over to our VM here, and I'm going to show you the initial route that I took when I was looking at this, which is just to open the debugger, put the breakpoint on create process internal, run until I hit it, and then see what's going on. That's not how to unpack this, but I'll show you what happens when you do that. So today I'm using a Windows 7 32-bit VM, and I just have X64 debugger installed here. I dropped the sample over and I called it Goot. You know, we know that it's Gootkit, or at least once I unpacked it, I could tell that it was Gootkit. So I just gave it that name, and I'm gonna run Process Explorer as administrator. Okay. All right, so let's open up our Goot sample in X64 debugger here. We're using the 32-bit version of it, so it's X32 debug. We'll just drag it over here, and we're gonna set a breakpoint on create process internal. And this is like a tip that Greg sent to me on Twitter, where you can actually just set a breakpoint from the command line here. So we'll try that. BP create process internal W. All right, so we had to set a breakpoint on create process internal. It's just a little bit easier than clicking through all the symbols and stuff like that. You can just use the BP command. Thanks, Greg. Kind of cool tip, and I've definitely been using that recently. All right, so now we can just run our sample here. We hit the entry point, breakpoint, and then we run again. So we've hit a breakpoint on create process internal, and if we look on the stack here, we can see that we're actually starting a copy of the Goot exe with the -L command line parameter. So this is the next stage that we saw in hybrid analysis, where they're starting a new version of the process with the -L command line. So when I first looked at this, I thought, okay, well, I don't want to have to like follow each step in the chain with like a new debugger instance. So instead, what I want to do is I'm just going to kill this. I'm going to change the command line arguments here so that I pass the -L into this process. So it looks like the process that's running is the second one in the chain of the process tree. So let's try that and we'll see what happens. I want to reload that file. Then I'm going to go into command line options here, and I want to add a -L on the end. And then I want to make sure my breakpoints are still set. So I can do the same thing, but now when it runs the process, it's going to run it with the -L command line parameter. So let's try that again. We'll run. We hit the entry point, breakpoint, run again. We hit create process internal. And if we pop over to our CPU view, here's the first tip that something is not going to work here. So we can see that instead of creating a third process with no -L flag, this is creating that process with the -L flag again. That's definitely not what we saw in hybrid analysis. So if we like pop back here, the second process in the chain gets the -L, the third process in the chain has no -L. You might be thinking, who cares if it's only the second stage? Maybe they're doing some injection here. Maybe you can pull something out here. But the thing is, if you return from this create process internal call, you're going to see something not so good happens. So the created process will crash on you. So we can close that. And this process won't attempt to do any injection into that. So this was started running, it wasn't started suspended. So that's the first tip, that there's probably not going to be process injection. And the second problem is it crashed as soon as you ran it. So we know that something weird is going on here. So I'd say like 9 times out of 10, when you see a process tree like that and it is doing process injection, you'll be able to unpack it really quickly just using this trick. And we've shown this in other videos. But in this case, when you have a scenario like this where things are going kind of crazy, it's always worthwhile to take a look at it in IDA. So I like to open it up in IDA and find out what exactly is going on. And the first place I'm going to look to find out what's going on is for the create process calls to see what's going on there. Okay, so I've opened up the Gootkit binary in IDA here. I'm just taking a look here. It's brought us to the winMain, and winMain just calls one function. It jumps into this function over here. And we can see there's a bunch of interesting stuff here. So we see these like calls to the register with a couple D words or bytes in memory being pushed before the call. It looks like there's probably some obfuscated stuff here. Now, to make this go a bit quicker, I am going to use the hexphrase decompiler. So I'm going to F5. It's going to show us the decompiled C code, and that's going to speed this up a little bit. So you can see exactly what's going on here. You have these sort of byte arrays which are being passed to this function here, and then that is being assigned to a variable, which then is being used later on in the code as a function. So to me, that looks like they're dynamically resolving some APIs. That's what it looks like to me. I think the first thing to do here is to take a look at these byte arrays here. So it looks like maybe there's a like obfuscated strings. So if we just do an X for xrefs and we see like where these are used, we can maybe try and find where they're being decrypted. Actually, it looks like good first try. So here I see a nice loop. I see an XOR, a single byte XOR with another string. Man, it looks like this might be a really simple string encryption algorithm here. So it looks like this might be a key. Yeah, so there's a string here and it's being a single byte XOR'd with the binary string that we saw here. Okay, this is looking pretty straightforward here. So why don't we just do a quick test here and see if we can decrypt these statically. So in order to decrypt these statically, we're going to need the offset to the string. We're going to need a copy of the key string, and we're going to need the length of this binary string here. So sometimes they put the length in the string itself, but it doesn't look, wait, actually. Yeah, so it looks like the string length is actually hard-coded in the function. This is like amateur hour here. So we can take the length here, the offset to the start of the string. We can use the IDC get many bytes. So our data is going to equal IDC.get many bytes, the address of the first start of the string, the length of it, which is 0C. So in data, yeah, we have the data. So then why don't we grab the string? So we'll call that key. We'll grab the key here, and I'll just copy that string directly because it looks like it's the same for each one of these strings. So grab that string here, and we'll do equals string. We do for I in range 0 to len of data, and we're going to do a out plus equals char ord of data at I, and that is going to be XORed with ord of key at I, and of course the I needs to be modded by the length of the key, so len key, so that we just repeat over the same key length for each iteration here. I think that's good. Okay, out. Hey, look at that. Here, I'll make this bigger so that you guys can see. So we basically did a single byte XOR encryption with this key value here over the binary string, and the output was kernel32.dll. So it looks like, yes, they are going to do some dynamic API resolution, and these are encrypted strings, and my guess at this simple single byte XOR was correct. So now what we need to do is we need to make this quick little Python script into a function that we can call for each one of these strings and label them. So I'm just going to do that now, and then through the magic of time-lapse video, everything should be labeled nice. Okay, so now that we have all those strings labeled, I've also taken the liberty to label some of the variables in the function that winMain was pointing to. So if we hop over into that, you can see that some of these variables are labeled, and the reason for that is if we pop into our hexphrase view here and we scroll down a bit, you can see that indeed I was correct that these strings are being used to resolve APIs, and then the API is being stored in a variable. So in addition to using using the script, which I will link in the description below. I'll put it on a gist on GitHub so you guys can take a look at the script if you want. So in addition to using that script, I also relabeled these variables here. I just did it by hand because there's not that many of them. But after we've relabeled those, you can sort of look through this function here, and now with all the APIs labeled, it makes a lot more sense. We can see what's going on. And we can see at the bottom here, there's a -L being passed to a shell execute, which is creating a new process. So we can see that there's a -L being passed to that as a command parameter, and the process name is actually the result of get module file name. So that means like get the name of the current running process. So we can see that here is where we're actually starting that new process with the -L command line parameter. And here's the important thing. So we can see after we call shell execute, we actually sleep for 2000 milliseconds. So for 2 seconds, we sleep the program and then we exit. So whenever we see that second stage starting with the -L command line parameter, there's not going to be any injection into that, which is what we saw with the debugger. Now we also saw that that process crashed. So we'll have to take a look at like why that happened, but we'll get to that in a second. The important thing here is to note that when you see that -L being started, there was no process injection there, but there was this sleep for 2 seconds and then the parent process exits. So let's look and see if we can find another place where they're creating the process without the -L and see if that's where they're doing some process injection. So in order to do that, we're going to have to search for create process or any of those API calls, create process internal or another shell execute or something like that. So the first place I'm going to look is in the imports here, because even though some of the APIs were resolved dynamically, as I show you guys, some of them are also just in the import table. So it's kind of like a half and half here. So if I look for process, we'll see, yeah, so there is a create process here, which we can go and take a look at. So again, I'm going to flip over the Hexraise view just to see the decompiled stuff a little bit easier. So we can see with the create process here, they return the process information in this variable. And then later on in the function here, they actually write to that process with the data that's in this variable that I've named as inject data. So this is really standard process injection. So they write to that process and then they do a set context thread and then a resume thread. So that means that they're actually changing the context for the main thread to use the entry point of the data that they've written into that process. So now we've identified where the process injection is. Let's work backwards and try and find out why it wasn't being triggered and why the process was crashing when we ran it in a debugger. So let's see where this is actually called from. And actually, I'm going to relabel this function name here as create and inject. So if we look at the cross references, we'll press X for xrefs, and there's only run reference in this function here. So let's pop over that function. And we know that the first thing passed in here, we'll rename the variable as proc name here. We'll rename this variable as the inject data, so we can see what's going on here. So it looks like it's getting the process name. I bet this does, yeah, get file module name. So this just gets the name of the current running process. So we know that aligns with what we're seeing in the hybrid analysis. So they inject into another copy of their own process. So that makes sense. And this var inject data, which is probably the data that we want to unpack, right? So we want to see where does that actually come from. So it looks like it's coming from this variable here, which is returned from this function. So let's take a look at where this D word is also referenced. So it's referenced in a bunch of functions. So let's pop over here. So yeah, it looks like they're assigning something here. So they're assigning it some memory. Okay, so they're doing a read file. So what are they reading here? Create file. So what is this? Xrefs again. So what is that argument that's being passed in here? They're reading the okay. So did you guys follow that? They're basically reading in this file and they're storing the contents of this file. So the file that created the process, they're reading it into a memory segment, and then that memory segment is being assigned to this D word here. So let's pop back and we'll rename the D word, name D word content. Yeah, so then we can pop back here and then this starts to make a whole lot more sense now. So they're reading in the file contents of the current running process. They do some magic. So this is probably where they're decrypting some data from the file and then they inject it into the newly created process. So in order to get here, we'll probably try and find some APIs around this function that we can hook in our debugger, and then hopefully we can search through memory and find that PE section that has been unpacked and it's going to be injected now. So let's see where this was called from, because we still haven't figured out why it crashes. Actually, let's rename this first. So we'll rename it as wrap create and inject, and we'll go to xrefs for that. So it's only referenced in one function, and it looks like this We will name this wrap again. So we're just going up the call chain to try and find some logic where this would actually create a crash for some reason. So let's see where the xrefs are here. Okay, interesting. So this is the cool part about the packer that I thought was unique and interesting about it. There's two tricks here and we'll go over them one at a time. So the first trick is the interesting one. So it looks like they are creating a mutex using this random string here. And then the result of create mutex, they're checking to see if there's an error, and if there's no error, they return. They don't do anything. But if there is an error, they call create and inject. So what this means is they will only try and do process injection if another process is already running and has already set this mutex. So this is kind of a clever thing. So what they're doing is they run this process once, which creates these mutexes, right? And it'll create these mutexes and it'll get no error, so it's going to return. And then remember, at the end of the execution of that main function here, they sleep for 2 seconds, which I thought was weird. So what they do is they create the new process, they sleep for 2 seconds, and then that new process checks to see whether these mutexes are set. And because the parent process has already set the mutexes and it's sleeping, those mutexes will be set, so they'll get an error and then they'll do the create and inject. So what this means is if you're running it in a debugger and the process is dead, or you've only run one process, there's no process tree active, this will never trigger the create and inject. So I thought this was super clever because you could really bang your head against the wall because they're using create mutex, so it's not something that you would normally hook. So usually malware is using create mutex to make sure that they're the only process running, making sure that there aren't two versions of the same process running. In this case, they're making sure that there are two versions of the same process. So it's kind of like a flipping the whole concept on its head. It's really cool, in my opinion, at least. I thought it was really interesting. So what this means is that in a sandbox environment or in dynamic analysis where you're not running it with the debugger and it's just running, this will do the injection. So you shouldn't have a problem with that. But if you're trying to do it by hand with a debugger, you'll see that it's never going to work because you'll never be in a situation where you have the parent process frozen in time with the mutexes open and then you've attached to the child process. I mean, you might end up with that situation, but it's pretty rare that you would have a situation like that. So these mutexes will never be found, in which case they'll never try and do the create injection. So I thought that was kind of cool, and that was like number one. So we know now that what we need to do in order for this to work is we need to allow the process to run until it creates the mutexes, freeze it, then we need to start a new process, and we need to run that process with the debugger so that it'll actually catch these create mutexes. Or we could write some code to create the mutexes ourselves, whichever way is easier. But we know that we have to do that. Now the second trick is something that you guys might have already spotted when we found out how they were reading the file in order to inject it. The second trick is the reason why we get a crash. So let's go back and take a look at that function where they read in the file content. So we'll press X to get our xrefs. I think it was the first function. Yeah, so here's the trick. In order to read from the file, they use CreateFile, and then they use the handle from CreateFile. They get the file size, and then they read from that file handle. So let's open up the documentation for CreateFile on MSDN, and we'll see what these parameters are. So I actually covered this trick in another video, but I'll go over it again because, you know, it'll definitely get you a couple times. It got me on this one because I wasn't looking for it. So let's pop over to our documents here. Okay, so let's look at the arguments here. So the one that we care about is ShareMode. So if we go down to ShareMode, this dictates how the file that you're accessing with CreateFile can be shared. And so if you don't allow the right share permissions, you'll get a share violation or an error, and that's what's going to contribute to the crash. So if we look at the function here, our share permission here is 0. So if we look at the documents, what is 0 for a share permission? It prevents other processes from opening the file or device if they request any sort of access to it. Now here's the thing, our debugger actually already has a handle open to that file. So because of that, when you request 0 share permissions, so you say like, I want exclusive access to this file, you're gonna get a sharing violation failure because the debugger already has an open handle to it. So it's gonna say like, hey, I can't give you exclusive access. So that's why we're seeing the crash crash. Now, I showed you guys in a different video, which I will link below, how to patch this function out so that you always allow full sharing access. Because that's the best way to get around this, is just allow full share access, and then it doesn't matter how many handles are open to it. But in this case, we might want to take it a little bit slower. We can just put a breakpoint on it in the debugger and we'll step through it. So armed with this knowledge, we know that there's two things that we need to do now in the debugger in order to get our sample to unpack so that we can actually dump the memory out and get the unpacked PE. So the first thing we need to do is we need to start an instance of Gootkit and freeze it after it's set the mutexes. So we'll use one debugger to do that, and we'll just start it and then we'll freeze it in memory so that those mutexes are set. The second thing we need to do is when we're debugging the process that is going to do the injection, we need to put a hook or a breakpoint on CreateFile, and we need to change the share permissions on the stack before the function is called. So that's two things that we need to do. And then we need to keep the hook on CreateProcessInternal so that when that's called, which hopefully it is eventually, we can dump from memory the PE file. So let's hop back over to our debugging VM and we'll see if we can't get this all to work. Okay, so we're back in our Windows 7 debugging VM. And so the first thing we want to do is we want to run one copy of Gootkit and just freeze it out before it exits so that it has those mutexes set. So let's open up X64dbg here and we'll pull Gootkit over, and we still have the breakpoint set for CreateProcessInternal, so that's probably a good place to stop. So we can just run. We're going to hit the entry point, run again, and we'll hit the CreateProcessInternal. So we're good. So we're just going to let that sit there. I'll minimize the debugger window and we can see that it's running. So that means those mutexes are set now. So now what we need to do is open another copy of X64dbg, another copy of Gootkit. What we'll do here is we'll run until we get to the entry point of the PE file, so for the first breakpoint, and then we'll set a breakpoint on CreateFile A, which is where we have that crash. So let's run until we get to the entry point. Now the reason why I'm setting a breakpoint after we get to the entry point is because CreateFile might be called when you're loading other DLLs, like before the process has got to the entry point. So I want to get to the entry point first to make sure that if we do hit the breakpoint for CreateFile A, it is actually the CreateFile A call from inside the process, not from loading some DLL. So let's use our breakpoint trick. Thanks again, Greg. BP CreateFile A, and we'll just double check that it's set here. So we have one on CreateFile A, and then we'll run, and we've hit a breakpoint on CreateFile A. So let's go and take a look at the arguments on the stack. So the first argument is a pointer to the file that is the Gootkit file. So we know that we found the right one. The second argument is permissions, and then here is the third argument is the share value. So remember, right now it's 0, so it's going to throw an error because there's already a handle open. So if we change that to 7, which just means like share everything, so share read, share write, share execute. So remember your standard like Unix style permissions. So if we change this to 7 here, we should be able to return from the call without any issues. So let's see if we can run until return here, and we return back into our code. So it looks good so far. So now what we want to do is we want to run until we get to CreateProcessInternal, which the breakpoint is still set on this. Hopefully that'll be a create process without the L flag, meaning that it's actually the process that they're going to inject into. So fingers crossed. Let's do this. So we've hit the breakpoint for CreateProcessInternal, and if we look at the arguments that are passed to CreateProcessInternal, we have Gootkit without the L, so we know that this is definitely going to be the process that's injected into, and we can see that just reading through the arguments here, this is going to be created suspended. So this is definitely going to be a injected process. So if you guys remember from some of the other videos that I've done on process injection, you know that if the process options flag is 4, that means that you're creating it suspended. You know, that's a dead giveaway that it's probably going to be process injection. So it looks like we've probably got this at the right spot. Now what we need to do is we need to find that unpacked PE file that's going to be injected into this process in memory. So a quick trick to do this is to pop into your memory map here, and you can just do a find pattern and search for the header that is found in a PE file. So instead of searching for MZ, which might occur a lot of times, that's like the magic bytes for a PE file, you can search for the DOS header. So So the DOS header will change depending on what type of PE file it is, but in all of them, I believe the string this program, like that string, so this program will be in all the DOS headers. I think that's, or at least in most of them it will be. So let's search for that here and we'll see if we get any hits. So we get a couple hits. Now what I'm looking for is I'm looking for hits in memory that is not an image. So these look good, like these lower addresses here. So if we go and do like follow in our dump here, what's the base address for this memory? 1700. So let's go to our memory map here, 1700. Yeah, so this is not an image. This looks like allocated memory, basically. So when you find a PE in allocated memory that is not part of an image, see the image designations here for like this PE file, for this DLL, they're all image designations. This up here is not an image. It's allocated memory from the process. So the fact that we found a PE file in there is probably good news. That's probably the PE file that we want to dump out. But remember from when we were looking at this in IDA, there's going to be two PE files in memory. One of them is going to be the Gootkit file that they've read in order to extract some stuff. So remember when they do the create file, they also read that file into memory. So there's going to be that PE file, which will be identical to the Gootkit PE file. Then there should be a second PE file, which is the carved out PE file that they're going to inject into the new process. So we're looking for a memory section that has two PE files in it, and we're going to grab the second one. So let's go back to our references here, and you can see 1C, I believe if we go into the dump here, and what is the base address for this? It's also 17 4/0 hex. So that means that it's in the same memory segment here. So that means that this memory segment has two PE files in it. So let's dump this memory segment out to our desktop here, save that out, and we will carve out those two PE files, open them up in IDA, and we'll see which one is not the one that is the original packed file. So whichever one is not the original packed file should be the one that we're injecting into this process. Now this is kind of like a lazy way of doing it, and it seems like this is maybe a bit convoluted, but it's way faster than having to like walk the call stack back up and try and find, you know, where the actual memory address is pointed to in the code. This is just a faster way to do it. Even though it seems like it's taking a long time because I'm explaining everything, this is like a 10-second thing, right? Versus having to take a couple minutes to walk back up the stack. That's why I do it this way. So now let's pop over to our other VM, which has IDA running and it has a hex editor, and we'll carve out those two PE files. Okay, so I've just dropped that carved out memory dump onto desktop here, and we'll open it up in HXD here, and we'll carve the two PE files out. So let's search for MZ here, and it looks like that's the first PE file. So we've just erased the data at the beginning of it, and we're going to save this as PE_file1.bin, and then let's carve out the second one. So we'll do the same thing. We'll search for the MZ, find again. No, that's not right. So let's search for the string this program. Okay, and so that's a good example of why we search for the DOS string instead of MZ, just because there's a lot of erroneous MZs in the binary. So now we found the second one, and we'll do the same trick here. We'll just erase the beginning part of the data before the PE. Yes, we want to proceed, and we're going to save this as PFile2.bin. And then we'll look at these in IDA here. So we'll open a new instance. Okay, so this is PE file 1 open in IDA, and it kind of looks like the packed file. And once we get into it, so remember this from the packed file. So this is the packed file that was read into memory. So we don't want this one. So let's try and open PE file 2 and see if that's the right one. So we'll open that up. Okay, so this is PE file 2 open, and we can see it's a different PE file completely. It loaded clean. It has imports and it has strings. And so this looks like a stage 1 for Gootkit. So it looks like we have, after all of that, we've unpacked the first stage of Gootkit and we've carved it out as a separate PE file, which we can then run in our debugger. So to wrap this all up, what we did first was we checked in the debugger to see if we could do a quick process dump for process injection. But we noticed that wasn't going to work because we had the second process was not suspended and it was crashing immediately. So there's no way that anything could be injected into it. So we opened it up in IDA. We had to do a quick string decryption, which is really simple, single byte XOR. And again, again, I'll link the script to do that below the video in the description. So we had to decrypt some strings and work our way through that packer just to see what the tricks were. And the tricks were that they're using mutexes to determine whether a parent process is running with the same version of the process that is currently doing the unpacking. So there has to be 2 copies of the process running, otherwise the unpacker won't unpack. And then we found the second thing was that they're using CreateFile with no share permissions. So the fact that the debugger had a handle open to the file meant that you're going to get a sharing violation error, and that was what was causing the process to crash. So armed with that knowledge, we went back to our debugger. We set it up so that there would be mutexes running, so that there were 2 copies of the process running. So that got past the first trick. And then we set a breakpoint on CreateFile, and we changed the share permissions before the API was called, and that bypassed the second trick. And then we were able to stop on create process and look in the memory to see if there was an unpacked version of the PE file, which was then going to be injected into the newly created process. And that's what we're looking at here. So you might be wondering, like, why didn't I just let it inject into the second process and then use something like Scylla to dump that out? Well, the reason why is because it already exists in a nice, pristine, unmapped form in the memory of the current process. It's always better to just grab it before it's injected into the process, because it'll be cleaner, it's easier to work with, and you don't have to worry about unmapping it, or like, you know, maybe the imports are messed up or something like that. And you can see that it is pretty quick. The only trick was that there's 2 PE files, and one of them was the original PE. So we just had to discard that after we identified it using IDA. So now we have stage 1 of Gootkit, and in continuing with our trend here, we will leave it up to you guys to analyze that stage. I will link to it below. I've uploaded it to Malshare, so you guys can download that and play around with it if you want. So hopefully this has been helpful to you guys to add a few tools to your toolbox when you're unpacking stuff. Sometimes it's not quite as simple as stepping through it in debugger. Sometimes you have to kind of go and do a little bit of reverse engineering. Again, I don't like to spend a lot of time looking at packers in IDA because generally it's not what you're interested in, right? You're interested in the payload, but every once in a while it's necessary because there's some trick like this that isn't really standard. And now that we know this trick, in the future, if we see the same sort of behavior where a sub process is being created and it's crashing and there's no injection, we now know to hook CreateFile A and to look at the mutexes to see whether this trick is being used. So we won't have to go back to IDA in the future if we have the same problem. We can just do it from the debugger because now we know the trick. So again, hopefully this is useful. Thanks a lot to Patrick for sending in the sample, and thanks to everyone else who is sending us samples in the comments below and also over email and Twitter. There's a long list of them now, so we're slowly working our way through. And like I mentioned, we do have a special project that we're working on, so we're kind of splitting our time now between the videos and working on this other project. So with that, remember, if you're not subscribed, to subscribe down below and leave a comment. Let us know if there's stuff that you guys want to check out. So until next week, keep exposing the mechanics behind the malware and stay curious.